resume the topological matrix school. We will continue with Cecile Repelen, who is continue talking about interaction-driven insulators in flatband Moiré superlattices. So, Cecile, please, the screen is yours.
Great, thanks a lot. So hi everyone, and thanks for tuning back in. So today we continue our exploration of correlated insulators in Moiré superlattices. So this is a brief reminder of the general outline of the series of lecture, including what we did yesterday, which was an overview of some incompressible phases and their filling fractions, and how increasing the length scale in these Moiré superlattices helps you explore the Hofstadter butterfly physics, and also how in some Moiré superlattices, topology and interaction effect conspire together to give rise to ferromagnetism and quantized anomalous Hall effect. So that was yesterday. And today we're going to move on to some fractional filling phases. So strong correlations are going to be even more important in this case. And we're going to talk a little bit about symmetry breaking and a lot about fractional quantum Hall states. And I reserved the part about numerical signatures of fractional quantum Hall phases for tomorrow. So here is a slightly more detailed outline for today. So first we're going to talk a little bit more about flatband ferromagnetism in the context of lattice symmetry breaking instead of spin or valley symmetry breaking as we did yesterday. Then move on to fractional quantum Hall effect with an introduction to this phenomenon, so something quite general, and then see how the fractional quantum Hall effect can be realized in lattice systems. And this is what we call a fractional chain insulator. And finally, we will explore the possibility that a fractional chain insulator might be realized in magic angle twisted bialeographene line with HBN. So the exact same Moiré superlattice that we focused on yesterday, but this time at fractional filling, and we will explore the possibility of this phase with or without a magnetic field. So we start with a few more things on flatband ferromagnetism. And I call this section this way because you'll see that there's an analogy with flatband ferromagnetism, even though we're talking about a quite different type of correlated insulator. So first, a little reminder. Yesterday, we saw that quantized anomalous Hall effect and orbital ferromagnetism had been observed in magic angle twisted bialeography in the light with hexagonal boron nitrides at filling 3 of the conduction bands, which corresponds to this situation where this is the schematic representation of the conduction band in this model, in this system. So I remind you that here we, unless in the magic angle twisted bialeography without alignment with the substrates, here we don't have any Dirac cones, but we have a gap between conduction and valence band. So we can consider the conduction band in isolation and consider this filling 3. So we looked at the microscopic origin for this phenomena coming from band properties, namely the fact that these bands have a Chern number that's different from 0. It's a Chern number 1 in one valley and Chern number -1 in the opposite valley. Overall, this polarization, this valley and spin polarization or at least this valley polarization as observed in experiments, arises from interactions. So this is a spontaneous time reversal symmetry breaking that's due to the exchange interaction in the system, and that's often called flatband ferromagnetism. And this lecture, I believe, was quite closely connected to the lecture that David Goldhaber-Gordon gave later yesterday from the experimental point of view. So now I want to talk about something slightly different, but that can also be seen as a form of flatband ferromagnetism. And this is something that can arise in a Chern band when its Chern number is larger than 1. And when this is the case, then you can really think of the Chern C band as a Chern 1 band with a color degree of freedom and an SUC color degree of freedom. So it's a bit like having C Landau levels at the same energy, and maybe with a bit of bandwidth and so on, all the things that make Landau level different from a Chern band. And so there's a quite recent experiment coming from Andrea Young's lab in twisted monolayer bilayer graphene, where they claim to have observed a color polarization in a Chern 2 band. So there are actually, I think, probably other examples experimentally, but I'm going to focus on this one. So in twisted monolayer bilayer graphene, so I took this I extracted this from this paper. This is the band structure around charge neutrality, and you see that the conduction band has a Chern number equals to 2. And that results in a quantized anomalous Hall effect around filling 3 that has a Hall conductivity of 2. So far, this is exactly the same thing as we talked about yesterday in magic angle twisted bilayer graphene aligned with HBN, except that instead of having a Chern 1 band, you have a Chern 2 band. Now, what's new here is that there's an additional correlated insulator here that occurs at a filling 7/2, so 3 plus 1/2, and with a Hall conductivity of 1. And the authors have interpreted these two states as being, so if you take again the Diophantine equation that I was using yesterday, which is very generic, which expresses the number of electrons as a number S times the number of lattice unit cells plus another number T times n phi, the number of flux quanta. This first state is a filling 3, so S equals to 3, and a Hall conductivity 2, meaning T equals to 2. So this is interpreted as a spin and valley polarization in the conduction bands. Now, the next state at filling 7/2 then occurs at when you have a half filling of one of the bands. So S equals to 7/2, it's a fractional filling now, but T equals to 1 because the Hall conductivity is equal to 1. And this is interpreted as on top of the spin and valley polarization of the conduction band, you also have a color polarization of the Chern 2 band, which results in this Hall conductivity. So let's dig a little deeper in the theory of this state. So what's a Chern 2 band, or what's a Chern C band? So one way to understand this is to go back to Ranier orbitals. So as you know, if you have a non-trivial band, so a band with a non-zero Chern number, for example, there's no way that you can write down localized Ranier orbitals. So you cannot write down like a lattice system exclusively for this band with orbitals, Ranier orbitals that are localized in both directions. But what you can do is build some 1D Ranier orbitals. And that means that those 1D Ranier orbitals, they are plane waves in one direction. So they are completely delocalized in one direction and defined and characterized by a momentum ky, for example, and completely localized in the other direction, characterized by a an integer n here, or which corresponds to one specific position in real space. So this is actually very reminiscent of what happens in, you can think of this as your Landau orbitals when you're in the lowest Landau level and doing the Landau level problem and looking at the wave functions in the Landau gauge. You're going to have these plane waves in one direction, and you have exponentially localized wave function in the other direction. And what's quite interesting about the case where the Chen number is larger than 1 is that it's going to allow you to define a family of one-year wave functions. And that comes from this, this property here, which is that inserting a flux, which corresponds to shifting ky by 2 pi, is the same as shifting your one-year orbital by an integer c. So more pictorially, this is what you have in a Chen 1 band. You have one family of one-year orbitals in blue. And in Chen 2 band, you can define two families, the even one and the odd ones. And as you do this operation, every time that you add 2 pi to ky, you're going to jump, but you're going to always stay in the same family. So you're going to, for example, jump from this blue one to the next blue one, etc., and never go to the red one. So we can really sort of decouple these two families of states. And these blue and red colors, those are the same colors that I was referring to in the previous slide. So when you have a hard filling of a band like this, you can, in principle, fill only the blue orbitals, which is going to result in a state with Chen number 1, because yeah, you only have half the Berry curvature integrated over the whole Brilliant zone. Okay, but translation and color are intertwined in these systems, as is clear from this relationship. So really, this type of symmetry breaking, this type of color symmetry breaking, is going to correspond to a nematic symmetry breaking. It's going to break rotational symmetry. So you expect a stripe order. So this was quite well explored in these papers, and sometimes called a topological nematic state, other times called a symmetry broken Chen insulator. Yeah, so in any case, you do need interactions in order to polarize the system into one of the two colors. So you have all these types of symmetry breaking that take place at the same time. Okay, but in any case, even though you have fractional filling, you don't have any topological order because the whole conductivity in this system is an integer. So now we are going to move on to something that's really different, which is the case where you do have a fractional Hall conductivity, the fractional column Hall effect and its lattice realizations. So I'm going to start back from the basics. So here are our Landau levels again. So this is the single picture. So you know that's the spectrum that you get when you have electrons or charged particles confined in 2 dimensions in a transverse magnetic field. You get the spectrum that's made of levels called Landau levels. Each one is macroscopically degenerate, and the degeneracy is equal to the number of flux quanta n phi that goes through the sample. So it's convenient to define the filling fraction. We've used it before in the lectures, but here let's call it new. Yes, was there a question?
There is a question actually. So this happens for every C2 band? So
no, this does not happen for every. So I guess this is about the previous slide.
Yeah.
So this does not happen for every C2 bands because you. Well, for example, you can imagine that you have a large bandwidth in your band, and if the bandwidth is very large, the likeliest thing is to get a Fermi liquid. So you're going to get a metal. So really, it's going to depend on the interactions. So it's going to depend on the interplay of interaction in the band, if the band is sufficiently flat, and the Berry curvature distribution in the band, because you need to be able to separate it into these 2C=1 bands.
Okay.
Yeah, so this really very much depends on the specific microscopic conditions. Yeah, so going back to the Landau levels, so we define this filling fraction U, which is the ratio of n, number of electrons, divided by n phi, degeneracy of the Landau levels. It tells you how much your first Landau level is filled. Now going to the many body picture, if I take u equals to n, I have an integer number of Landau levels that are filled, then I get the integer quantum Hall effect. On the other hand, if the filling fraction is a fraction, not an integer, so then we have a partially filled Landau level. And for some very specific fractions, you get an insulator, you get an incompressible phase. And that's what we call the fractional quantum Hall effect, which is characterized by fractional Hall conductivity or fractional Hall resistivity. So this is a hard problem. Typically, the strength of interactions V is much smaller than the cyclotron energy, which is the energy gap between the Landau levels. And you can really work within the lowest Landau level approximation, assuming that nu is smaller than 1. So you can work with this effective Hamiltonian, which is just a projection of interactions, probably a Coulomb interaction with maybe some screening into the lowest Landau level. So to gain insight into this problem, which is a many-body problem for which this not really you can't really do any perturbative approach. It's a strongly correlated problem. So there are a number of approaches, and I want to talk about two of them that are very powerful. One of them is numerical, using exact diagonalization and GMRG. And the other one is variational, using model wave functions. And in particular, what's I think something very unique about the fractional quantum Hall effect is you have model wave functions that have no variational parameters and that are quite simple, that actually capture extremely well the low energy physics of the fractional quantum Hall effect. So I'd like to talk a little bit about this now by talking about the Laughlin wave function. So where does this wave function come from? So if you are working in the infinite plane, you can write down one-body wave functions in the symmetric gauge, or at least it's practical to do so. And they can be written like this, as the complex coordinate z at the power m, where m is the single particle angular momentum, times a Gaussian factor that is written here. Now I'm going to consider n particles now in the lowest Landau level, or rather n electrons in the lowest Landau level at position z1 to zn. And I start with the simplest many-body state that I can write, which would be the integer quantum Hall effect at nu equals 1. Then I would have n fields orbitals, where n is the number of electrons, and also n is the number is equal to n phi, the number of flux quanta, or the number of lowest Landau level orbitals, rather. So this is just a Slater, the wave function is a Slater determinant, which if I simplify it, I can write it down as a, so it's a Vandermonde determinant, which comes down to this Jastrow factor. And I still have my Gaussian factor here at the end. The Laughlin wave function corresponds to a filling fraction 1/m of the lowest Landau level, and is written on very similarly, except that you have this power m for the Jastrow factor, and you still have your Gaussian factor accompanying this overall wave function. And this wave function is it's really nice and very powerful for many reasons. So first of all, many observed fractional quantum Hall states have a filling fraction 1/m with m odd, because you need this factor to be antisymmetric to have a fermionic wave function. So in particular, nu equals to 1/3 was the first experimentally observed fraction. It has a quite large gap. And the Laughlin state captures the physics at this fraction really well. In fact, it has does a really large overlap with the ground state of realistic Coulomb interaction projected onto the lowest Landau level, or even with some corrections coming from Landau level mixing and other things. And maybe most importantly, this is the same topological order. And finally, this Laughlin wave function is also the unique densest ground state of a model interaction. So it has a quite simple parent Hamiltonian. So I mentioned topological order, but so topological order means that we have a state that corresponds to a finite correlation length. So if we're talking about energetics, it corresponds to a gapped state when you're using a local Hamiltonian. And also it has excitations that are anyons, that are neither bosons nor fermions. So let's look a bit at the quasi-holes of the Laughlin states. And for that, let's start from a density profile of the Laughlin states. So very similarly to the quantum Hall effect, the fractional quantum Hall effect is a phase that doesn't break any symmetry, or at least doesn't break any spatial symmetry. So you see this plateau of the density in the middle. If you add one flux quantum, this is actually how you create quasi-holes in such a system, and this will create a local charge depletion with a charge E/3. So this quasi-hole has a fractional charge. And a thing that's super convenient about the Laughlin wave function is that you can write down the ground state wave function, but you can also write down the quasi-hole wave functions very conveniently. So this is the wave function for a Laughlin for one quasi-hole, which is located at position W1. And you can do the same thing with the second quasi-holes. And I'm going to assume that the two quasi-holes are at positions W1 and W2 that are very far apart. And in those conditions, you can show that the wave function writes down like this with a normalization factor here that doesn't depend on W1 and W2. And with the rest of the wave function, what you see appearing here is that if you change the position of the two quasi-holes, W1 and W2, you're going to have a non-trivial phase appear. So this corresponds to the fractional statistics of the Laughlin quasi-hole. And those two things, fractionalization of charge and fractionalization of the statistics of the charged excitations, those are characteristics of topological order, and they actually they defined the topological order associated with the Laughlin state. Yes, so I also want to show another hallmark of topological order, which appears when you do some numerics. And this is quite useful when, well, you have a Hamiltonian and you may not know what is the nature of the ground state. Is it an insulator or not? If it's an insulator, then does it have any topological order or not? So here I'm showing you the low energy spectrum of the Coulomb interaction as projected onto the lowest Landau level for a system with 8 fermions and 24 flux quanta. So that means I have a filling fraction 1/3. So this is not the largest size you can do with exact ionization. You could do a few more electrons, but okay, this is what I had on hand. So this is the energy, first few eigenvalues, and the x-axis corresponds to the center of mass momentum. So it's a quantum number that is very convenient to label your many-body eigenstates of the Hamiltonian. And what you see here, the main features that I want to focus on these plots are those three. Sorry, the Zoom window is bugging me here. So yeah, are those 3 ground states, which are degenerate, and then you have a gap to higher energy excitations. And actually, if you do the same thing for the system sizes, smaller or larger, you're always going to see this feature of this threefold degenerate ground states separated by a gap to higher energy excitation. And this gap, well, it's even though you have a very small system, this gap converges relatively quickly. So you see very few fluctuations with system size. And this, even though the system is super small, you're actually quite close to the thermodynamic limit, which comes from the fact that this Laughlin state has a very small correlation length. So it's a correlation length which is 1 point something times the magnetic length. And notice that the 3 ground states are exactly degenerate. This comes from a symmetry in Landau level systems that's associated with the magnetic translation algebra. If you didn't have this magnetic translation algebra, maybe because you are in the lattice system or something like this, but you still have like a Chan number, you may not always have an exact degeneracy. You could have a small lifting, but you expect that this lifting will be resolved at the thermodynamic limit. But in any case, these threefold degenerate ground states on the torus geometry, that's a hallmark of topological order, and especially of this 1/3 Laughlin state. And I will talk a bit more about signatures. In principle, this threefold degeneracy is not enough to fully diagnose the Laughlin topological order, but I will talk about that tomorrow. Yes, question?
Yeah, so what is the Hamiltonian for this data?
Yes, so the Hamiltonian is a Coulomb interaction. So yeah, just plain Coulomb. I believe here I just used Coulomb, but you could use some screening additionally. And you project it onto the lowest Landau level. So you project it in the basis of the Landau orbitals in the lowest Landau level. All right. Right. So yeah. So as I said, we will talk a bit more about this fractional quantum Hall signatures, these numerical signatures in the lecture tomorrow. Yeah. So this was a bit of a crash course on the basics of the fractional quantum Hall effect. And I want to add two more components that will be really necessary when it comes to analyzing the possibility of such states in Morris superlattices. One of them is the presence of a lattice, and the other one is the presence of additional degrees of freedom, like spin. So let me start with the lattice. So a Landau level is very similar to a Chern band with a Chern number 1. That's quite clear at this point. And I can make this analogy between the Landau levels and the band structure, and I can compare, for example, the conduction band with the lowest Landau level. We have two well-defined bands with, if you fill them up, you have a whole connectivity of 1. There are going to be two main differences between those two objects. And one is energetic, it's the bandwidth. And the other one comes from the eigenvectors. So the Berry curvature, quantum geometry, and all these things. So, and both of these properties will have consequences once you turn on strong interactions. So let's start with the role of the bandwidth. So if I'm going to assume that I can work in the lowest Landau level limit, meaning I can project everything down to the lowest Landau level, and the equivalent thing to do for a Chern band would be the projection to the conduction band. So depending on the system you're working with, this may or may not be an approximation that you want to do. But I think it's justified to do it in some cases at least. The difference between the two systems is that you have a non-zero bandwidth, which if I write down the Hamiltonians in K-space, this is the additional bandwidth. And so maybe this expression here is the answer to the previous question from the previous slide of what is the Hamiltonian. Here I've written it in K-space. So V of Q would be 1 over Q times some numerical factor. And then you have the density interaction, normal ordered. And this is a projected density. So if I write it down in terms of the operators that create and annihilate an electron at momentum k and k plus q, I need to use this form factor here, which is defined thanks to the single particle eigenvectors of either the Landau level or the Chern band. So what's the role of the form factor? If I write it down in the Landau level case, what I can see quite easily, if I, after replacing these UK with the Landau orbitals, is that this does not depend on K. So this is a quantity that only depends on Q, the distance in K space between the two wave functions, but it's something that doesn't change in K space. And this is what's different in the Chern band. The form factor corresponding to this overlap depends on Q and K. So if you'd like, you can think of this as an interaction that's not completely homogeneous in K space. In fact, it would be homogeneous if the Berry curvature and the quantum metric were uniform, as is the case in a Landau level. So because of these two differences, we can think of the Landau level as being a very convenient limit of a Chern band. So this is the limits of a zero bandwidth and of a uniform interaction, of uniform form factor for the interaction. But away from that limit, we're not sure when we add strong interactions to a strand band, we're not sure whether we're going to get a fractional quantum Hall state or not. So we need numerics in order to determine whether this state, which we call the fractional chain insulator, arises or not.
Yeah, there is a question. Mikel Garcia is asking, when you project to the LLL, the particles feel an effective Hamiltonian. For this insulator, are you taking the Coulomb interaction as it is, or is it screened?
Yeah, I mean, I haven't really specified anything for now. So the only time that I showed you numerics was the previous slide, and I took an unscreened Coulomb interaction. Then you can take what you want. This is a phenomenon that's, I'm talking about the fractional quantum Hall effect, that is very robust. So if you start screening the interaction, you're still gonna get the fractional quantum Hall effect. And for fractional chain insulators, I believe it will, it might depend on the screening length, right? But other than that, I can't really make any very general statement.
Okay, thank you.
Right, so that was fractional quantum Hall effect and lattice properties. Now, fractional quantum Hall effect and spin. In my introduction, you saw that I made a simplification to use a spinless case. In fact, electrons have a spin, and this creates a really rich physics for the fractional quantum Hall effect. Even from the level of wave functions, you can generalize the Laughlin wave function, which was done by Halprin, and what you'll get is those Halprin wave functions that are basically products of Laughlin wave functions. So a first Laughlin wave function for the spin up, one for the spin down, and one that couples together spin up and spin down. And some of these wave functions will correspond to states that actually are incompressible states in the fractional quantum Hall effects and can be observed. So let's take two examples of this physics of the fractional quantum Hall effect while considering the role of spin. So let's review the 1/3 fraction, which we've already talked about. And this one is spin polarized. In fact, it's a ferromagnet, and it's in many respects, it's very similar to the μ=1 quantum Hall ferromagnet, except this time it's a fractional Hall conductivity. It has topological order, but from the point of view of spin, it's quite similar. So I've written again the Laughlin state now, emphasizing the role of spin and the fact that it is spin polarized. And I want to look at the μ=2/3 thinning fraction, because it's quite interesting and it's going to be helpful for the rest of the lecture. Because here you have, it's interesting because you have two main candidates. So maybe the simplest thing you can think of if you just know the Laughlin wave function is just to do a particle Hall conjugation. So that's still going to be a spin polarized wave function. But you have another candidate, and this candidate is a spin singlet. And it's not directly written as a Halprin wave function, but it's in the same universality class as the Halprin 2-to-1, meaning factor 2 and 2 for spin up and spin down, and factor 1 for the coupling between the two. And in terms of, so those are wave functions. And when you play with Hamiltonians and energetics and you ask which one is the ground state, the answer is it depends. And it depends on the Zeeman field. So in fractional quantum Hall experiments, you have a strong magnetic field, but depending on the G factor of your material, you may have a smaller or larger Zeeman energy associated to your system. And actually, if you have a G = 0, if you have no Zeeman energy, the ground state is the Halprin spin singlet. or the states associated with it. So it's a spin singlet. And if you have a larger Zeeman energy, you're going to fully spin polarize and end up in the other phase, the Laughlin, if you'd like, particle hole conjugate Laughlin phase. And this is something that is seen both in experiments and numerically as you change the Zeeman energy. So you see, this is an example of how spin can introduce another degree of freedom that makes the physics of fractional quantum Hall effect even richer. So how does all of this fit within the context of Morris superlattices and especially magic angle twisted bialeographene aligned with HBN? So let me set the stage for this. So first of all, that's just a reminder. We had in this system, we had a narrow band with a Chern number 1. And this was seen in experiments as orbital ferromagnetism at a filling fraction nu equals 3 of the miniband. Yes, question.
There is a question, anonymous attendees, asking how large are the Zeeman fields? To even get the fractional quantum Hall effect, you need very large fields, right?
Yes, so the magnetic fields are very large. I mean, they're like 10 Tesla, let's say, although you can find a fractional quantum Hall effect at slightly smaller fields. But even at those large fields, the Zeeman energy is quite small. If you to say that, you need to compare it to the interaction strengths. So the typical so the Zeeman energy varies like around 0.3 times B, the magnetic field, while the energy, which is given, the interaction energy, which is given roughly by E square over epsilon LB, varies like something like, I forgot the exact number, but at least 10 times or more times square root of B. So even though it grows more slowly, the prefactor is so much larger by a factor of something between 10 and 100 that the interaction energy is actually much larger than the Zeeman energy.
Thank you.
Okay, I hope this answers the question. Yeah, so we have this narrow band. So since we have a Chern band, which is almost flat, so we probably have, we have strong interactions. We already know that. Why couldn't we have a fractional quantum Hall effect in this Chern band? And I want to consider one specific filling. And I'm going to tell you why. So I want to consider the filling 10-thirds because I know that valley ferromagnetism or orbital ferromagnetism, however you want to call it, was observed at filling 3, but also for filling slightly larger than 3, including this 10-third filling represented here. And this 10-third corresponds to 4 minus 2/3, which means that I can walk in the whole picture within a single Chern band at filling fraction 2/3. So this makes the problem slightly easier to think about. And that's going to make a link with what I talked about of the physics of 2/3 earlier. So yeah, can we find some fractional quantum Hall physics? So to do this, well, some will or have tried to do the experiments. I can do some numerics to try and see if it has a chance to work. So for that, you can do exact diagonalization. And so let me tell you about the model that we're using. So we start from the Bistrisser-McDonald model, to which we add a a sublattice breaking term corresponding to the alignment of HBN. Okay, so that's what we talked about yesterday. And that gives you the single particle wave functions in the conduction bands, which I'm calling UK. And then my Hamiltonian, I'm running it in K space because that's how, since K is conserved, you do the calculation in K space. It allows you to take advantage of those translation symmetries. So I'm writing down the Hamiltonian K space. I have Coulomb interaction screened, and I have density operators here, normal ordered. This still corresponds to the projection. And then I have a non-zero bandwidth, and it's somewhat artificial, but I am, okay, so I don't, maybe I don't care too much about being very realistic, and I want to see if I'm in the right ballpark energetically. So I'm using this W quantity as a way to just control the bandwidth. So as I said, V of Q is the screen Coulomb interaction. Rho tilde Q is the total projected density operator, where I can see that I have my form factors here as I had earlier. And we're going to assume valley polarization because it's seen in experiments, so it's a sensible assumption, but we're not making any assumption on spin, and we're working at spin fraction 2/3. Yes, there's another question.
Another question. This Q now corresponds to the wave number of the Moiré cells.
Yes, so it's within the. Sorry. It's within the mini Brilliant zone. Yes. So the so actually you can yeah, it's the wave number of the Moiré cell. That's correct. Okay, let's see if we can see some results now. So I'm specifying the relaxation ratio. So I believe it's been, I haven't talked about it, but it's been introduced in previous lectures by Oscar Wafek and by Andrei Bernevik last week, and maybe by others as well. So this is the ratio of interlayer tunneling from A to A for W0 and from A to B for W1. And we're going to consider a value of 0.8, which is what's typically we think of as realistic. Yes.
There is a question by Nish Verma. Can you comment on the gauge freedom of U and K? I don't know what's.
Yeah. So I this okay. So this is what I defined in the last slide. Yeah. So when you get those wave functions, the computer is going to pick a gauge randomly for this UK, and it's actually it's not something that you really need to think about too much, as long as you always work in the same gauge. So what's important is, when you do the diagonalization, the single particle diagonalization once, and that gives you all the UKs in a given gauge, and you always use the same one for when you compute your Hamiltonian. So this is what it's used, and then you don't change.
Thank you.
Right, so here are some hexagonalization results. So here I'm showing the case for 10 electrons in a 6x5 lattice. So it's the number of Moiré unit cells. So total 30 Moiré unit cells. And this was obtained by assuming valley polarization. So actually the first result, even before showing those spectra, I should say that what we obtain, we see that the ground state, when we look at all the spin sectors, because spin is a conserved quantum number, so we can look at the energy spectrum per total spin value. And the one with the lowest energy is the spin polarized one. So we get a fully spin polarized state. And in this sector, this is the energy spectrum that we get. And you see here that we have 3 states that are very close in energy, separated by a gap to higher energy states. And actually, this window here shows the corresponding extrapolation to thermodynamic limits, and this is the number of Murray unit cells. So thermodynamic limit would be 0 on the left here. This is the extrapolation of the gap depending on system size. And this is the extrapolation of degeneracy lifting for the ground states here. So you see that more or less this goes to 0 as expected for topologically ordered states. And this gap remains finite. And very importantly, you have this nearly threefold degenerates or threefold nearly degenerates ground state that's typical of a 1/3 Laughlin state. We looked at other signatures. Again, I'm not talking about this today to keep things within one consistent topic. So yeah, we found evidence for spin polarized Laughlin fractional chain insulator, or Laughlin fractional quantum Hall states at filling fraction 2/3. And we checked the influence of bandwidths, and we saw that it is robust up to maybe 10 to 15% for bandwidths over interaction ratio. We also looked at the effect of Berry curvature. So I'm realizing now that I don't have much time left, but I just wanted to emphasize that this is this band, so Berry curvature, this is something that's a band property basically. And actually you can tune it extremely well in twisted bieliographene by tuning the relaxation ratio from the chiral limit, W0 over W1 equals to 0. And for the details of what the chiral limit means, I refer you to this paper to some realistic value where the fluctuations of the Berry curvature in the mini-Brunel zone are much larger. And you see that so this is the Berry curvature fluctuations now as a function of relaxation ratio. It becomes much larger for more realistic relaxation ratio. And so this is something that's been known for a while about fractional chain insulators, is that they require relatively uniform Berry curvature fluctuations. So it's quite a good sign that even for the small but somewhat larger Berry curvature fluctuations in the realistic range, that we still see a fractional chain insulator state. But it's something more surprising that we saw, which is that there is a spin phase transition that's controlled by the Berry curvature fluctuations. Indeed, when we went to the chiral limit, we realized that we still got a fractional quantum Hall state or fractional chain insulator, but this time it was a singlet. And as we changed the relaxation ratio to increase the Berry curvature fluctuations, then we saw that phase transitions towards the fractional quantum Hall ferromagnet that I mentioned earlier. So this is the more specific data for different system sizes. So this is very reminiscent of the phase transition that occurs in continuum systems between the Halpern spin singlet and the spin polarized particle Hall Laughlin. Basically, you have exactly the same phase transition, but instead of being controlled by a Zeeman energy, it's controlled by the Berry curvature fluctuations, because here there's no magnetic field, so there's no Zeeman energy actually. And I just wanted to finish by saying a few words about experiment in that field. So no fractional Chan insulator, no fractional Hall state has been seen in the complete absence of a magnetic field, not in twisted Valeo graphene and not in any other system. But we're getting closer, I think, because with some recent experiments have reported a fractional Chan insulators for fields as low as 4 Tesla, which is much lower than the previous experiments that we had realizing fractional Chan insulator, which was 30 Tesla. And in that newer experiments, basically the magnetic field is thought of as just being there to renormalize the Berry curvature to make its fluctuations a little smaller, rather than being completely essential to the topology of the band. Okay, so I think I'm really running out of time now, so I should stop. I should stop here with just a small summary of all of these things. Yeah, I'm happy to take any questions.
Thank you, Cecile. So actually, there are 2 questions in the Q&A box. Mikel Garcia is asking, we saw that an RG treatment of the flat bands flow toward the chiral limit. Isn't then reasonable to think that you can tune the range of the tunneling parameters to a smaller value?
Yeah, so if I remember correctly, it flows to the chiral limit, but not quite, because the parameter controlling that flow is not, well, large or small enough, depends on the direction, to go completely towards the chiral limit. So the experimental parameters are what they are, and I think yeah, it seems like a value of around 0.7 or 0.8 is relatively realistic. So I guess yeah, maybe if you take into account the effects of this RG treatment, maybe you realize that it's actually smaller. Yeah, it's a possibility.
The other question is, what is the abelian or non-abelian Berry curvature you showed?
So it's the okay, what did I show? Yeah, it's the it's the complex part of the quantum metric tensor. So I don't know, I'm not sure how to better answer this question.
Yeah, perhaps there can be a discussion in the Slack channel afterwards.
Yeah, for sure.
I see no further questions, so we thank you again, Cecile. Thank you very much for this talk. And
Thanks.
we see you again tomorrow, right?
Yes.
Yeah.
See you tomorrow.
See you tomorrow. Thanks. So our next speaker is Thoe Su. Thoe, are you there? Can you please unmute yourself and share your screen?
Yeah, I'm unmuted. And is my screen sharing?
Yeah. So Thoe Su is talking on behalf of Professor Kashiras, and she's continuing about the talk of yesterday. So please, the stage is yours. You can start.
Thank you for having me here. And my name is Dian Zhou from the Katsura's group at Harvard University, and I will be continuing Professor Katsura's talk yesterday. And my focus will be on moire of moire superlattices, which is a new type of system that we've been focusing on, and there has been a lot of experimental interest as well. So during this talk, feel free to interrupt me with questions, and I'll try to monitor the Q&A session, but in case I don't, the host will help me out. So don't be shy to ask questions, and I'll be happy to address them. So just a quick review of yesterday's talk by Professor Katsuras. He introduced a single particle model for twisted bilayer graphing. And this is a really framework that was developed by our group using a multi-scale approach. So all of our calculations are based on density functional theory. And we use DFT to extract parameters for our more simplified models, but running density functional theory itself is not really practical because, as we know by now, that all the twisted system has a really large system size and the land scale is very large. So, to solve for the relaxation and the electronic properties, we developed this framework that Professor Katsuras introduced yesterday. For the relaxation, we have this local configuration space approach to solve for the relaxation pattern in real space, and on the right is a framework to solve for the electronic structures in those twisted bilayers, and those are basically at different scales, and one is built on the other. And so I'm using the same framework to solve for the properties in twisted multi-layered moire of moire system. And in particular, my presentation will be focusing on these two blocks. And the left is, of course, the relaxation pattern of those moire of moire system. And on the right, I'm using a low energy effective model to solve for the electronic structure of those systems. So again, there are a lot of experimental interests in those multi-layered van der Waals heterostructures, and the first of which is the consecutively twisted trilayer graphing, which is also the focus of my earliest work. And in the system, this picture, which Tim also showed yesterday, Professor Ko-Wang's group from Minnesota observed correlated insulating states and superconducting-like states near the half filling of the moire of moire superlattice. And the reason why we say it's a moire of moire superlattice is the really low filling factor. The filling factor here is around 10 to the minus 10, which corresponds to a very large lattice that has the periodicity of around 85 nanometers. So this is really an order of magnitude lower carrier density compared to the TBLG system. And of course, there is a more recent experiments by Pablo Herrero's group and Philip Kim's group on this alternatively twisted trilayer graphing or mirror-symmetric trilayer graphing, meaning that the first layer and the second layer are twisted in the same direction instead of the opposite direction in the first case. And just to note that if the system is perfectly mirror-symmetric, this is not a moire of moire superlattice because everything would happen at the moire scale. And indeed, in the experiment, the observation is made at the moire scale. However, in an experiment, it is really hard to make sure that the first layer and the third layer are perfectly aligned. So in that case, we would have a moire of moire superlattice. And I'll make more comments about that and how to make connection to the experiment. And finally, there is the bilayer graphene and BN heterostructure. So the system here, here shown in the picture is AB bilayer graphene encapsulated by top and bottom boron nitride. And this experiment in Pablo Herrera's group observed ferroelectricity and hysteretic behaviors in the system. And also yesterday you heard from Professor Gordon's group, who also observed these hysteretic behaviors in twisted bilayer graphene HBN system. So in both types of systems, there are moire of moire superlattices due to a twist angle and a lattice mismatch. So here is a quick outline of my presentation. And first, I will be introducing the system of interest. And I'll be talking a little bit about the geometry and how to understand the length scale of the system. And then I'll go into modeling the relaxation model and the electronic structure, respectively. And even though our model is completely general and it can be applied to any type of systems, I'll use twisted trilayer graphene as an example, but of course I'll mention other systems along the way as well. So twisted trilayer graphene, the way we can understand it is through, again, this picture of interacting Dirac cones. And you've already seen this picture from Professor Katsura's talk yesterday. In twisted bilayer graphene, the we already understand at this point that the interacting Dirac cones would form, would cause hybridization between these two cones because of the proximity brought by a small twist angle. And at the magic angle, the Fermi velocity would be further reduced because the band would flatten out. And this would imply strong electron correlation and signatured by an enhanced density of states. And of course, the picture is largely the same if you have a third layer, but now the interaction can happen at both pairs of the Dirac cones. For example, if we consider the interaction of Dirac cones between layer 2 and layer 3, it can be affected by the presence of the third layer, which is the layer 1. So effectively, we have to consider both of them. But because of the additional tuning knob, this will make the system more interesting, and it gives it an additional degrees of freedom to control the presence of the correlated states and as well as the density states flattening. So this is very interesting, but from a modeling point of view, it is actually a very difficult system to deal with. And the reason is that the system is aperiodic, even in the continual limit. This is very unlike the twisted bilayer graphene. And in the case, even in the case where a periodic approximation exists, the system size is really large. And to understand this, we can watch the following movie. And this is similar to the one that Professor Gordon showed yesterday. First, we start by rotating only one layer. We can clearly see that there is an approximate periodicity that changes smoothly as the twist angle changes. But now if we start to rotate the third layer, in this case, you would observe more complicated patterns that evolve non-smoothly as a function of the twist angle. And you would also notice that even though you observe these large scales, each one of them are not identical. So as a result, we generally do not have a supercell approximation. So now we can take a closer look at, we can be more quantitative about the length scales in the system. And to understand it, we have to look at different harmonics of the moire of moire pattern. And so just as a quick review, we can go over how we obtain the moire pattern in TBLG. For example, to start with, if I define the matrix G to be as follows, and the G1 and G2s are the primitive reciprocal lattice vector that spans the monolayer Brillouin zone. So this is the monolayer graphing. And the G1 and G2 are the column vectors of this matrix. And then, of course, the real space lattice would be given by the inverse of these, the G vector. And now with the rotation, the monolayer reciprocal lattice vectors are rotated. And I assume layer 1 is the only one that's being rotated. So the G1 matrix would be defined as the rotation matrix act on the G matrix, and then G2 from layer 2 would be the original G matrix. And now the Moire pattern, bilayer Moire pattern, can be calculated by simply taking the difference between these two matrices. Basically, we want to calculate the distance between these two reciprocal lattice vectors that are slightly rotated from each other. So this G12 that spans the reciprocal space of the Moire cell can be written as G1 minus G2, which is basically the R theta 1, 2 minus the identity multiplied by G. And of course, the Moire pattern would just be, again, the inverse of these G vectors. And this prefactor would basically give you the Moire length. So this is how we obtain the bilayer Moire pattern in real space. And so actually in general, taking the difference between the G1 and G2, you can have a factor in front of it, meaning a more general case, sorry. Meaning that a more general case would be basically, apologize for the technical difficulty. Here it is again. Okay, now it's back. Okay, so a more general case is actually that you can take linear combinations of the difference of the Moire pattern, namely that M G1 minus M of G2. And basically the dominant Moire pattern would be when the difference between these two terms are the smallest. But actually in a bilayer graphing, the distance is the smallest. One can clearly see that the smallest distance happens when n equals to m equals to 1. And because in this case, the magnitude of G1 and G2 are equal. Now in trilayer graphing, we go through basically a similar process to take the difference between these G vectors, but now it's between the G vectors of the two Moire patterns. And in this case, we notice that the Moire lengths are different and they're also rotated from each other. So there is no guarantee that the Mn is 1. So basically you can take any linear combinations of M and N and find the dominant Moire length by looking at the smallest distance. And here is what the picture A is showing. So what I'm plotting is these different peaks correspond to different Moire harmonics and as a function of twist angle by fixing the second twist angle to be 2.8 degrees and sweeping the first twist angles. And the first thing we would notice is that depending on the twist angle, the dominant Moire length come from a different harmonic. And also, we can look at some examples of these peaks. For example, there is a range of regions where the 1-1 harmonic would clearly dominate in the absence of other peaks. For example, this point B in the figure will correspond to the following real space picture. And we can clearly see that on the top, there is indeed a distinct trilayer-Moiré pattern, and the bottom figure corresponding to a small tiny region here, which shows the bilayer-Moiré pattern from the two layers. And these two bilayer-Moiré patterns are very close in length scale, but they are slightly rotated from each other. And we can look at another point which corresponds to a dominant peak at the 2-1 harmonic, meaning one twist angle is roughly twice as the other. And here, again, in figure D, we see another dominant Moiré pattern, but again, now it's between a 2x2 Moiré cell and a 1x1 Moiré cell. So the interference pattern happens at a different harmonic. But there is other regions where there are a lot of, for example, in this region where there are a lot of competing harmonics with similar length. And this is the following picture. And if we look at the picture on the top, you can see that there is no clear length scale that describes the trilayer-Moiré pattern. And this is a more difficult case because really clearly there is no approximate periodicity. And so we can also look at the Moiré length as a function of both twist angles. And in this picture, we are basically only plotting the dominant Moiré length as a function of theta 1,2 and theta 2,3. And these dominant lobes are those figures with a very clear, distinct Moiré length, but in between are the angles where many twist angles are competing with each other. And from this figure, you can see that one observation you can make is that the Moiré length scale does not evolve smoothly as a function of the twist angle. And the second thing you can observe is that there is no one-to-one correspondence between the Moiré length and the twist angles. So experimentally, if you determine the area of the Moiré cell, I cannot tell you exactly where the twist angles is, but I can only constrain myself to a contour on this plot. And we can also apply the same technique to calculate the Moiré length in alternatively twisted trilayer graphing, or when L1 and L3 are twisted in the opposite direction, in the same direction. Typo here. And you get a similarly complicated picture. Okay, so now with the understanding of our system, let's move on to solving for the relaxation pattern of such a system. And we will see how the domain would form in a trilayer system. And our goal is, of course, to minimize the total energy as a function of the displacement vectors from the relaxation. And our total energy has two terms. The first being the interlayer term, which describes the interaction between layers, and it comes from the layer misalignment. And as Professor Katsouras talked about yesterday, the equilibrium stacking in the system is AB and BA stacking, which means that locally the atoms would want to go to this equilibrium stacking. And the second term is the intralayer term, which describes the elastic energy from the surface deformation. And so this is very good and clear, but of course our difficulty is, again, the aperiodicity. So instead of looking at the real space, we go to a more local description of the system in order to have a more accurate description without a supercell approximation. So as an example, here is a picture of the real space, and we can zoom in near the three spots locally here. And say we are interested in the position of a red atom here in the picture. And the way we deal with it is that we draw a unit cell around the red atom and look around in this local environment, this local unit cell. We'll immediately see that there will be a blue atom and a green atom from the two other layers. So now to describe the position of the red atom, what you can do is you can draw two vectors from the red atom to the blue and green atom of the other layer. And these two vectors would form a configuration space that uniquely describe the position of this layer, this atom in layer 2. And note that technically there is a third vector, but it's starting from the red atom itself and back to itself. So this vector is always 0. And so this two vectors form a 4-dimensional configuration space that allow us to describe the system instead of the real space. And there is a one-to-one correspondence between configuration space and real space, and has been shown in this math paper. And now we can formulate our problem in configuration space by discretize the space. And one can also show mathematically that the mapping between real space to configuration space is uniform by ergodicity of incommensurate systems. So with this space in mind, we now write down what each term would be like. First, the interlayer term would be described by the generalized stacking fault energy, which is the same as the bilayer. And we extract the GSFE from density functional theory. And of course, this is a generic description for any type of 2D materials. And here I'm showing examples of graphing at WSC2 of 2 different orientations. And the interlayer energy is the sum of every pair of interlayer interactions between layer 1, 2 and layer 2, 3. And also note that the argument is the relaxed local displacement vectors. So this big B is defined as the sum of the original configuration little b plus the little u. So this is really a relaxed position, meaning that if the atoms are relaxed to a lower energy configuration, this B is say like an AB stacking after relaxation, the energy cost will be reduced. And the second term, the intralayer energy, is basically described using linear elasticity theory. And again, we sum over 3 layers, and the C here is the elasticity tensor, which we also obtain from density functional theory by performing strain and shear to a unit cell and do a quadratic fit. And finally, of course, we have to integrate over all configurations. And finally, this gradient of U is the strain tensor, which is defined in terms of real space gradient. And the strain tensor, there is a convergent factor between real space and configuration space. And that convergent factor is what gives you the twist angle dependence. Okay, so now let's look at what the relaxation pattern looks like after the energy minimization. And first, we can look at, we can try to understand the relaxation pattern in configuration space. And here is an example of what it looks like. And I'm looking at the relaxation between layer 1 and layer 2 averaged over the layer 3 configuration. And similarly, in B, I'm looking at the relaxation between layer 2 and layer 3 averaged over layer 1 configuration. And the first thing you notice that the relaxation strength is much larger when the corresponding twist angle is lower. So this is similar to the TBLG case. In the bilayer case, that's also the trend. And the second of all, you will notice that the relaxation would point towards ABBA stacking. And this is also not surprising because as we mentioned before, the relaxation tends to minimize the total energy by pushing the atoms to equilibrium stacking. And this relaxation would also form domain walls between each pair of layers as follows. This is, of course, between neighboring layers is similar to bilayer graphing. But to really see what's going on, we have to go to the real space, and which will give you a better idea of the relaxation pattern of the system. And so to go back to real space, we use the following mapping. And the idea is for every real space position R, we find what the local configuration vector is, which we find this B vector. And for every B vector, we have a relaxation vector that corresponding to a layer L at this B. And then this will be our real space displacement vector at this R. And we perform this mapping for every real space R. And that's how we obtain the real space relaxation pattern. And so now we can take a look at the following system with these two twist angles. And of course, the rotation convention is given right here. First thing, we can look at the relaxation pattern on the Moray scale. The unit cell is given in a tiny box here near the origin. And the top figure is the relaxation displacement vectors, and the bottom figure is the curl of the relaxation, meaning how much the displacement vectors rotate. And we notice that near the origin, there are rotations that is the same direction as the global rotation directions, and this is to minimize the AA areas in order to minimize the total energies. And we note that there are relaxation indeed happen at the corresponding Moray scale between layer 1 and layer 2, as well as layer 2 and layer 3. And now if we zoom out even more, now the black box right here corresponds to the view that we just saw. And now we see some even large scale that emerging at a different scale, which is the Moray of Moray. So this is showing that there is large relaxation. Relaxation happen at a large scale, and domain would form on this large scale as well. But if you look closer to each one of the distinct or the global AA area, each one of them is different. And so just for fun, we can take another step back and zoom out even further. And what we will see is that there are even longer scale that's emerged. And so the moral of the story is that the system is truly incommensurate. And when you keep zooming out, there will be more and more land scale emerging, and this will really never stop. And it shows our model's capability to capture the aperiodicity and the true incommensurability of the system. And it's suggesting that this large scale moray cannot be ignored in any sort of model. Well, another thing, the system is different than the bilayer system is another special case where the two twist angles are equal. And so in this case, naively, one would expect that the relaxation between layer 1 and layer 3 to be identical because of the symmetry. And indeed, there is a solution that preserves this symmetry where you see that the relaxation in layer 1 and layer 3 are basically equal and opposite. And in the middle one, at the global AA spots in the middle layer, there is basically no relaxation or no rotation. But that's not the whole story, because if we look at that there is another case where another solution exists that breaks the twofold rotational symmetry along the D direction. And you see that there are this large pinwheel kind of motions going on that breaks the layer symmetries between 1 and 3. And another solution exists with the opposite rotation direction. So this is surprising, but actually we can understand it from the point of view of competition between misfit energy and the intralayer elastic energy. And so what this pinwheel motion is doing is basically it redistributes the AA spot's density. And by reducing the density of the AA spot, it gains, reduces also the misfit energy cost. But however, the pinwheel motion will cost elastic energy, meaning that, but here is in figure A, we're looking at the total energy as a function of the twist angle. So both twist angles are equal. And we notice that when the twist angles are small, both the symmetric type of solution and asymmetric solution coexist. And the asymmetric solution is slightly lower in energy. And this is suggesting that the reduction in the misfit energy by the pinwheel motion would outweigh the cost of elastic energy for those smaller twist angles, because these pinwheel motions do not happen very often given the large Moiré-Pomeré scale. But as the twist angle increases, the density of the global AA spots would increase. And that would mean that if you keep having this pinwheel motion, the elastic energy cost will become greater and greater. And so it's so the reduction in the misfit energy is not enough to compensate for the increased elastic energy. And here there is a transition point, critical twist angle at 4.58 degrees, where this asymmetric solution almost becomes symmetric, and the two solutions have equal energy. And this feature is a feature of a bifurcation point in differential equations, and it's really a characteristic of a trilayer system. And so lastly, of course, I want to talk about a system that has attracted more recent interest, this kind of alternatively twisted trilayer graphing. This is a project in collaboration with Professor Pasupathy in Columbia University, and I'm not going to talk about experimental detail here, but I'm just to show our relaxation results. And basically, what we are showing here is the local twist angles with these two sets of global twist angles. And so the variation of the local twist angles are calculated based on the relaxation displacement vectors. And we see that the relaxation happens form a triangular domains on the bilayer scale and also hexagonal domains on the large trilayer scales. And the first figure here is showing the local twist angle between layer 1 and layer 2. And the second figure shows the local twist angle between layer 2 and layer 3. And the third figure here is taking the difference between them. And what it means that this is telling you the twist angle between layer 1 and layer 3. And so what we observe in this last figure is that there are large regions with zero twist angle. And meaning that after relaxation, the system would, the layer 1 and layer 3 would really align themselves and form these large uniform domain. And the experimental implication is that even if your first layer and the third layer are slightly misaligned, after relaxation, there will be large local regions where they are. So perhaps that in this kind of situations, the Moiré scale physics would be observed, and if you consider this large carrier density. And so another thing we can do with this is we can use a single number to quantify the local twist angles by looking at the separations of the local AAA spots. And here in the figure on the right, I'm showing you the local twist angles converted from the local AAA separations to a single twist angles. And we clearly see the formation of 3 distinct domains. And the regions where the twist angles are increased are what we call the twistons with larger local twist angles. And then there are blue regions where their twist angles are reduced, which we call the magic morays. And of course, there is a domain wall, which we call the solitons. And from the distribution of the local twist angles, we can clearly see that the 3 distinct regions in this figure. And this trend matches with experimental observation, which I will not go into detail here. Okay, so now let me go into my last section of this presentation, which is to model the electronic structures in these moray of moray superlattices. And our model is this momentum space continuum model. And here is again our system with alternatively twisted trilayer graphene. And here is the real space tie binding Hamiltonian. And basically what we do is we perform a block expansion to this real space Hamiltonian in momentum space. And similar to the bilayer graphene, there will be a mini Brillouin zone near at the scale of the bilayer moray length. But what's slightly different is that now you have 2 different moray Brillouin zones that are different in size, and they're slightly rotated from each other. And note that in our model, we do not ignore this small rotation, unlike some other more simplified model. And now, after this transformation, these 2 models are essentially mathematically identical. But a simplification we can make, because we're only interested in the low energy physics, is that we can take a finite cutoff around the Dirac point and performing a low energy expansion. So again, we start from this real space tie binding model, which has 2 terms, the intralayer term, which is the monolayer tie binding model that describes the near neighbor hoppings. And also the interlayer term that describes the hopping between different adjacent pairs of layers between layer 1, 2 and layer 2, 3. And now we perform a plane wave expansion. And of course, the intralayer Hamiltonian would just be the tie binding Hamiltonian of a monolayer in momentum space that we learned in solid state physics class. And the interlayer term is slightly more trickier, because as you plug in the plane wave expansion to these 2 orbitals, there is a small rotations between them, which gives you a selection rule on the off-diagonal terms of the Hamiltonian. So formally speaking, the Hamiltonian can be written as a 3x3 block, with the diagonal blocks being the intralayer terms and the off-diagonal blocks being the interlayer terms. And the intralayer term in our model, we use a rotated Dirac Hamiltonian. And the interlayer term is given in the following expression. And the ij describes the different layers, and alpha beta describes the different sublattices. And the most important part of this expression is the delta function, which dictates the scattering selection rule, meaning the momenta from the different layers and how they can couple to each other. And if we take the low energy limit, and this expression can be reduced to the familiar Bistritzer-McDonald style model with omega 0 and omega 1, as many have talked about in the school, to be the relaxation modified interlayer tunneling vectors, with omega 0 describing AA and omega 1 describing AB tunneling. So how is this different than the bilayer case? Well, again, we have to resort to this delta function, which is the scattering selection rule. In the bilayer graphene, we only have one set of selection rule, namely the K1 plus G1 equals to K2 plus G2. And this is to say that if the difference between the layer 1 and layer 2 momentum degrees of freedom are differed by a Moiré reciprocal space lattice, the scattering is allowed. And this relationship gives rise to a very clear momentum space lattice on the Moiré scale as in figure A. So we have basically a momentum space crystal, and it's periodic. But now with a third layer, we have a second selection rule that we have to basically obey, which is K2 plus G2 prime equals to G3 plus K3. And so basically, if you plug in the K2 from the first expression, we would obtain a relationship between the layer 1 and layer 3 momentum degree of freedom. And as we do that, we see that all the degrees of freedom are interconnected. And as a result, the number of degrees of freedom get really large. And this is what the figure B is showing. That's all the allowed momentum degrees of freedom from all three layers. And this is still with a finite cutoff. And we see that those degrees of freedom do not overlap with each other, and which results in a very large basis set. So then if this is the case, how do we perform a cutoff? Well, in the bilayer case, for example, if we start from scattering from layer 1 at the origin, we can scatter just by a reciprocal lattice vector of layer 2. And say, if we want to perform a cutoff with this orange circle, that means that we can throw out everything outside of the circle. And so this point right here can be discarded. But now the situation is slightly different with a trilayer. First, we start from the origin and scatter by a reciprocal lattice vector G2, which brings you outside of the cutoff circle. But then the second selection rule tells you that you can again scatter by a reciprocal space lattice vector of the layer 3. And the sum of these two can bring you back into the circle again. So this momentum cannot be discarded anymore. And this very simple analysis shows us there is infinite number of degrees of freedom within a finite cutoff. And so our solution is, instead of just constraining the scatter momentum or the sum of these two vectors, we also constrain the magnitude of these, the individual G vectors. So again, we would throw out this degrees of freedom here. But of course, the result of this is that we threw out a lot of relevant degrees of freedom, and there's no guaranteed convergence mathematically. But for the purpose of our work, we are only interested in the Van Hoff singularity's position and the magnitude of the density of states. And we have shown that these properties are basically constant as you change the cutoff radius. So we are okay there. Okay, so here let's look at the results of density of states evolution as a function of the twist angle. Well, the first thing we do is we keep the twist angles to be equal and consecutive, and we look at the density of states evolution as a function of twist angles. And we see that as we decrease the twist angle from large to small, the two Van Hoff singularities approach each other, and the separation between the Van Hoff singularities reach a minimum at around 2.1 degrees. But in this case, we notice that on this color scale, the magnitude of the Van Hoff singularity peaks, even though the separation is reduced, the magnitude is comparable basically to the large twist angles. Well, does it mean that the system is not as interesting as the twisted bilayer graphing? Not so quick. We can look at a more general case where we keep one twist angle fixed at 3 degrees and change only one of the twist angle from large to small. And in this case, we see that the two Van Hoff singularities, again, they approach each other as the one twist angle decreases. And finally, they touch at this value. And in this case, the two peaks completely merge. And also the magnitude of the density of states is an order of magnitude higher compared to the large twist angle values. And note the log color scale here. So how do we understand the origin of such a density of state enhancement? Well, to see that, we can map out basically the density of states as a function of both twist angles. And what we're plotting here is basically the density of states maximum and the separation between the two Van Hoff singularity peaks. And what you would probably notice on the first side, that the most prominent feature is that there are density of states enhancement that has some asymptotic behaviors that's approaching to this dashed line, which also corresponding to the reduction of these separation between the two Van Hoff singularity peaks. And this dashed line is actually the magic angle of TBLG. So this makes intuitive sense, because if we think about it, when one of the twist angle is really large, that means that the third layer is decoupled from the other two layers. And the system is effectively reduced to a twisted bilayer graphene with a decoupled monolayer. So naturally, the magic angle of that system would be at the magic angle of the TBLG. And so this makes us think that these enhancements are due to a TBLG perturbed by an external potential from the third layer. And to confirm that hypothesis, we can perform a perturbation theory calculation to extract the effective Fermi velocity. And what we can do is we can truncate the Hamiltonian to the first shell by keeping one degrees of freedom from layer 2 and 3 degrees of freedom each from layer 1 and layer 3, which gives us a total of 7 states. And here is the basis of the wave function. And we want to solve for the zero energy states, and which gives us the following form for the spinor components. And now if we solve for the effective Hamiltonian, write down the effective Hamiltonian write down the effective Hamiltonian of the system to the leading order in Q. Here is an expression you get, and the coefficient of this expression is the renormalized Fermi velocity with the following form. And if we're interested in the density of states enhancement, we will set the renormalized Fermi velocity to 0, meaning that the band is perfectly flat, which gives us the expression of alpha squared 1, 2 plus alpha squared 2, 3 equals to 1/3. This is our magic angle condition for the twisted trilayer graphene. And if we take the limit of one twist angle to be infinity, say like if we take theta 2, 3 to be infinity, this will give leads to alpha 2, 3 to be 0. And so that means that alpha 1, 2 squared equals to 1/3. And this is exactly the magic angle condition in the TBLG system that's derived by Bistritter McDonald in 2011. Okay, so back to our density of states. So here in this figure, actually the solid line is plotting this magic angle condition, and it matches very well with our density of states enhancement, except for near the diagonal regions, where the twist angles are nearly equal to each other. And we also notice that there are density of states enhancements in this region compared to all the neighboring regions. So this is suggesting that these perturbation theory picture is not sufficient to describe these density of states enhancements. And this is a consequence of the hybridization between adjacent bilayer pairs with a shared middle layer, meaning that this is a really a Moray scale hybridization and cannot be sufficiently described by a perturbed bilayer picture. And of course, we want to look at the band structure as well. Here is one example of band structure with the following set of twist angles. And of course, just looking at it, you will see that all the bands are really messy, and a lot of them are nearly overlapping with each other. And of course, this is the consequence of the complex basis set of the trilayer model, because the basis sets have many non-overlapping degrees of freedom, and we don't really have a Brillouin zone. So I'm just cutting through a high symmetry line. So this is not really a periodic, periodic band structure. But this gives us some idea of what's happening. And despite the messiness of the bands, we will notice that these bands near the Fermi level are actually pretty flat. And indeed, that corresponds to a sharp peak in the density of states. And because this point is near the magic angle as we predicted. And the third thing you would immediately notice is that the system really do not have a band gap as in the TBRG system. So the lack of band gap in TTRG has also been shown by Professor Brunnerwick's group in this paper. So the system has to be a perfect metal. And so, okay, so now with all the theory, we can compare with some experiments. And the first check we did is checked against a STM paper that was published in 2018. They measured the density of state spectrum basically of the system. And our model is able to produce the correct peak positions that's measured from the STM data. And what's probably more interesting is a system with correlated states. Here is a picture from Professor Kowang's group on twisted trilayer graphing. And the experimental consequence of a lack of band gap is that at the full filling, we do not have an insulating gap. But what happens is that the behavior, if you look at the temperature dependence of the resistance, it is basically temperature independent. So near the full filling, you have a semi-metallic behavior instead of insulating behaviors. And second of all, you can look at the correlated behaviors that happens near the half filling. And this will correspond to enhancement of the density of states. But again, as I mentioned in the very beginning of this presentation, that there is no one-to-one correspondence between the Moray cell area and the twist angles. So just from the full filling vector, I can only constrain myself to a contour on the twist angle phase space. So this contour that I'm pointing to right now is all the allowed values of twist angles. And the colors are showing you the density of states maximum on this contour. So based on the area and the observed correlated behavior, we know that the density of states need to be enhanced. So we can conclude that we need to be basically on this area of the twist angle space or this one. They're related by asymmetry. And even though we cannot uniquely pin down what the twist angle is, this gives us some idea of where you are in this phase space. But of course, this is based on the assumption that these correlated behaviors are indeed coming from electron correlation. And finally, lastly, I want to also point out that our model is completely generic, and it can be extended to other systems, even though that I'm only showing you results for graphing. You can extend it to a TMDC system by modifying the intralayer term, of course, also the interlayer term. But the intralayer term would now have a stacking dependence as derived by Wu in 2019. And you can also apply the model to graphing HBN system by including the effective potential from HBN as derived by Moon and Cochino in 2014. And this is something that we have been working on. Okay, so this brings us to the conclusion, and I showed you the relaxation pattern and the electronic structure of these moire of moire superlattices, and making connections to the experiment. And I would like to acknowledge my collaborators in helping with the projects, and of course for you for your attention. And I'll be happy to take questions now.
Thank you. Thank you. So let's see if there are questions. Actually, I don't see questions in the Q&A box. I don't know if somebody is taking the opportunity to ask a question. I am not a theoretician, so this kind of calculations take me a bit offline. But my question is about the computational resources which may or you need to carry out these relaxations. I assume you have to define a very huge superlattice with a huge amount of atoms, right?
Yes. So the relaxation calculation is not atomistic. So meaning that we look at the local configuration space and discretize the configuration space. And it's indeed very computational intensive because our configuration space is 4 dimensions. So in bilayer, you can discretize the space, and the number of degrees of freedom would be scaled as n to the n squared. But now in trilayers, it would scale as n to the 4th. This is a really a huge increase in the number of degrees of freedom, and the computational cost will be hugely enhanced. In most of the calculations that I show, I discretize the space using n equals to 100A. So the total degrees of freedom is 100A to the 4th. And that means that on the cluster, I have to run it for several days with like 36 cores. So it is really a computational intensive calculation.
Yeah, let me, I just wanted to mention something very briefly. This is not a large number of atoms. It's a large number of local configurations. I just wanted to make that distinction. And that's the advantage of the configurational space approach, because we cover, by what Zoe was describing, we cover a very huge number of local configurations, possibilities. So this is just one configuration with many atoms, which would have been just one example, right? So that's how we cover all this phase space.
Okay. Thank you. Thank you so much. I see no further questions, so we acknowledge again Zoe for her beautiful talk. Thank you. And so we come to the break. We will take a half an hour break until 5 European time, and then we will reconvene for the last talk of the session of this afternoon by David Gordon. So thank you again, and I hope to see you in half an hour. Hello.
Hello. Sorry about that. I set 2 alarms and neither of them went off. So
What time is there? It's like 8 or?
yeah, it's 8 o'clock, but unfortunately I stayed up most of the night. But that's but I will give me just a minute, and I will.
Yes. And take your time. Okay.
Sure. Okay, I think that should do it.
Okay. You can share your screen, perhaps.
Yes, just 1 second, and I will do that. Um, all right.
Looks beautiful.
Great. So, so I can start now.
Yeah, so welcome back again. So let's resume operations. David, please, the stage is yours.
Great. So for those of you who were here yesterday, I talked about the that when my group attempted to reproduce superconductivity in twisted bilayer graphene, the first time that we tried it, we got something, we didn't see superconductivity and saw something different that I think ultimately was maybe even more interesting. The first orbital magnet at or near zero magnetic field, that is a magnet that worked the way that that we were told in our first physics classes, that there was just a little loop of current and lots of little loops of current that were oriented that together add up to a big loop of current. And so instead of the magnet being made primarily out of spins, it was actually made out of circulating currents. And just to be clear, since then we have seen superconductivity in twisted bilayer graphene a number of times. The difference was because we had inadvertently done something different in our stacking. Specifically, we had aligned the twisted bilayer graphene nearly perfectly to one of the 2 layers of hexagonal boron nitride that was protecting it. And so instead of the boron nitride acting as something really inert, it was playing playing a role in shaping the state of the system, changing the band structure. So, so that's where we left it last time, and I told you that today would be about another attempt to reproduce now the orbital magnet. So just as a reminder, there was superconductivity and correlated insulators, I just 1 second. I attempted to hide slides, but I seem to get the wrong one. So let's try this again. All right. Well, I won't go backward. We saw orbital magnetism, as heralded by a very strong Hall effect around zero field that was hysteretic, and as of today, this is known to exist in 2 samples in the world. And
hi, David. Hey,
yes,
David. Yeah, we see a blackout. We have a blackout, so I don't know
right.
what appears.
Thank you.
Now it's okay. So apparently there was one slide. Is not. We didn't see the last slide. But
all right. So I'm not sure why that was. I'm now seeing it as blackout. Also, can you?
No, we cannot see that. Perhaps you want to skip. But the next one, oh no.
You can't see it?
No, actually, we don't see anything now.
All right, let's stop the share. I will.
Okay.
So I will try to multitask for. Well, no, actually, I'm not going to try to. All right, here's what I'm going to do. See if this. I'm sorry for
no problem. No problem.
the challenges. I think that I can. All right. I suspect that this will do it. Right. Right. Let's. Maybe this will be the charm. So, can you see it now?
No, we see you. We see you.
Yes, you see me, but yes, this time it will work. And all right.
Yeah, now it seems to work.
All right. Yes. So, so the modern world sometimes comes together. Thanks very much, Santiago, and everyone for your patience. And let me just repeat from yesterday that if you have questions, don't hesitate to ask while we're going along. So as I said yesterday, all these samples with their beautiful, exquisite physics are made still using a relatively old-fashioned, and I would call artisanal technique. It's done, one at a time by students, and that involves taking the best single crystals you can find of some layered material, in this case graphite, putting a simple piece of Scotch tape. If you look at it, this is Scotch magic tape. That's actually the version that Gaiman Novoselov used originally, and it actually is still one of the best to use. Peeling off, folding it over a few times, sticking it down on a simple substrate, peeling it off, and seeing what you get. And And when it works well, sometimes you get some very thin layers, including, in this case, 1 layer, 2 layer, 3 layers, 4 layers of graphene. And if you want to look at monolayer, for example, which is used to make twisted bilayer, then you would just focus on this part and continue your fabrication and etch away the rest. So, then you use a little piece of polymer that's a bit rubbery and sticky, a layer of different polymers to pick up part of this monolayer, then rotate, pick up another part of the monolayer, and you have your 2 layers of graphene. And I've skipped the other layers involving boron nitride, but you get the idea. The issue with this is that you're stuck with whatever flakes you find. And secondly, the specific method for making this twisted layer, at least that most people still use, is called tear and stack. Picking up part of it and abruptly pulling off the surface to rip it, and then moving over another part and rotating. And you can imagine that that's not going to give you totally reproducible results. It has the advantage that you can hope to define the angle between one part and another, because you know that this is a single crystal of monolayer. And so when you align part of it to another part, but with a rotation between the two, you can hope to set the angle between them. But you can see that it's not going to be totally reproducible, and indeed, we don't always get the same angle. And so this I showed you this before. This is a stacking station that my student Aaron Sharp built after visiting Pablo Herrero's lab. This field is very generous about sharing knowledge and helping people out. And you can see it's nicely built, but it's basically mostly a set of micrometers that you can carefully adjust to position things in many axes. And then there are two critical axes, one the rotation and one the approach between two parts that are motorized, and so we can control them really finely. In any case, I mentioned that this leads to every sample is different. So now I'm going to tell you about the next different sample. This is just trying to, yeah, there we go. So this was an attempt to make two twisted layers aligned with boron nitride. In this case, we got a twist angle between the two layers that was a bit larger than we wanted, not 1.2 degrees, but nearly 1.4 degrees. And that's, you might think, all right, that's not a very big difference, but actually in the world of magic angle graphene, where even 1/100th of a degree can matter, this is a big difference. And specifically at this angle, you wouldn't expect a very flat band. The band now has enough dispersion that Coulomb energies are not going to dominate over the bandwidth. So when you look at sweeping the filling of the band from completely empty to completely full through the charge neutrality point, you can see that at the charge neutrality point, the resistivity is a sort of familiar 2 kiloohms. It's not 100 kiloohms. There's no gap opened here. And in addition, there aren't strong features at, say, half filling of the electron part of the conduction part of the band, or half filling of the whole part of the band. So all of this looks like, all right, we just got the wrong angle, and this is going to be a relatively it's not going to show the magnetism because it's not a very flat band, but it's going to be pretty mundane. But now we can turn on a magnetic field. And here's what happens when we turn on a relatively modest magnetic field, 1/10 of a Tesla all the way up through 2 Tesla. Now, first I should mention that this is a resistivity, a longitudinal resistivity, so a measure of the scattering in the sample, not the Hall resistance. And secondly, this is on a log scale. So if you look at this, there's a lot going on, and I'll pick that apart. But the most dramatic thing that's happening is roughly around half filling of the electron band or the Hall band. There's a huge magnetoresistance. So in the end, we've seen up to about a factor of 300 in some cases. And that's very unusual to see a really large magnetoresistance. And when it occurs, usually the context it occurs in is a very simple one in a sense. Some of you probably learned solid state physics from Ashcroft and Merman's book, and they go through the calculation of what happens if you have 2 populations of carriers, 1 electrons and 1 holes, and they have almost the same density, just opposite polarity. And what is the Hall effect and what is the longitudinal resistance? And that's a case where you get a very large magnetoresistance, but that involves having 2 densities that are almost perfectly matched and opposite. Here we're getting this large magnetoresistance. So that occurs, say, in a semi-metal, a slightly compensated semi-metal. Here we have this very large magnetoresistance over a large range of density. And so there's no way that we can stay at the same density everywhere there. So that was the first thing that really jumped out for us. If we look in these regions, here's a cut where we're sweeping magnetic field, and you can see this very large magnetoresistance. It's actually approximately quadratic, and that's the same that you see in a compensated semi-metal. And then you start to see oscillations that look like Shobnikov-de-Haas oscillations, so the formation of Landau levels. And if we look closer, we get our second surprise, that the Landau levels seem to appear in pairs. That I'm not showing this in terms of filling factor, but if I did, this would be an integer filling factor, and we'd have features split to above and below that integer filling factor. So that's again very unusual and surprising. And so let's put together these different ways of looking at the data in a color map. So last time I showed you a color map and then broke it down and did line cuts from it. In this case, the line cuts that I showed you were first line cuts along the gate voltage axis, changing density at different magnetic fields. And you can see this is the region where magnetoresistance occurs, where there's a very large color change from 0 magnetic field to even a very small magnetic field. And then the other line cut that I showed you was a line cut at fixed density, but sweeping the magnetic field. And when we put these together, what you can see is that these Landau levels, which I can now make assignments, these are what you would expect to be the dominant Landau levels are, I'd say 4, 8, 12. This comes from the fact that that you have spin and rough spin and valley symmetry in the system. So every Landau level is in a multiple of 4, and then it's familiar that you can get that symmetry weakly broken, and so you also get say 2, and then a little more subtly 1 and 3. So all of that looks reasonable. But then when you start to see what happens when these Landau levels enter the region with strong magnetoresistance, you can see that they seem to split in two. And it occurs on both the hole side and the electron side. And that's really strange, and no one had reported that before. And there's one other strange thing that sort of jumps out here.
David,
yes,
there is actually a small question. Yes, is the magnetic field perpendicular or parallel to the sample?
Yes, I apologize. I should have said this field is perpendicular to the sample, and I'll say one thing very near the end about parallel fields. But thank you very much, Danielle. So for those of you who are used to looking at diagrams that are sort of like this, first of all, I referred to Landau levels, and those are things that occur when you have a magnetic field perpendicular to a 2D sheet. But also there's more richness than just electrons in 2D in this system. It's electrons in 2D, but with it's not a Jellium model. It's not electrons that are just unpatterned, but they're living in a periodic potential, a spatially periodic potential. Now that's true of all electrons in materials. After all, we have crystal lattices, but in twisted bilayer graphene, as you may remember from last time, we form a moire structure. The two lattices, because you have two lattices that would be matched if there was no rotation angle, but because of the small twist, the two go in and out of registry. They beat against each other, just like if you play two musical notes when an orchestra is tuning up, you play two musical notes and they're slightly out of tune with each other, then over time, they go in and out of registry, and the frequency of that so-called beat note tells you how much out of tune the two notes are. Similarly, the smaller the twist angle, the more slowly in space these two lattices go in and out of registry. And for the angles that we're considering, the spatial period of this at magic angle, it's around 10 nanometers. Here it's a little bit less than 10 nanometers, but we get this pretty large spatial period lattice. And then we're putting on a magnetic field that can actually thread substantial flux through each plaquette of this lattice, through each copy, each unit cell, effectively, of the lattice, so that at the maximum magnetic field we're able to apply, it's maybe a third of a it's around a third of a flux quantum per site. And some of you may know that what I've just described is the Hofstadter problem. Douglas Hofstadter, who, when he was doing his PhD physics thesis, considered this problem of a periodic lattice and a magnetic field normal to the plane, and found that you get all kinds of not just the regular Landau levels, but all kinds of lines that cross each other. But what they don't do is split. They don't. There's no. Well, his calculation didn't calculate resistance, but they wouldn't produce a strong magnetoresistance. And if you look more closely, when these splitting lines cross each other, there's an ornate structure where this line comes, it jumps as it crosses the other line, and then it jumps back when it crosses the second one. So there's all this ornate structure. So let's try to understand what's going on here. I told you that, so we have these three sets of phenomenology, and I told you that the model that one might imagine for this is something that looks like a periodic potential with a magnetic field on it, but that does not give this exotic behavior. And so if we can maybe get a clue by looking at what's happening to the Hall effect as we tune gate voltage. So near the charge neutrality point, the Hall effect gives you can extract a density that just goes linearly with gate voltage. That's what you expect normally. Then in these regions where we get the strong magnetoresistance, what we see is a Van Hove singularity. We cross over from electron-like behavior to hole-like behavior. And if you remember last time, that was something that occurred at 3 electrons per Moiré cell. Here it's occurring around and close to 2 electrons per Moiré cell, although I'm giving density not in electrons per Moiré here, but in 10 to the 12 per centimeter squared. And when we go through the Van Hove singularity, we've gotten a jump in density, but now it keeps going up. So what you see is that this region is indeed, as we sort of thought it might be, a region that's pretty near a compensated situation, or the region that's shaded is the region where we're crossing over from electrons to holes. So, so that's maybe matching what we thought might give magnetoresistance, though still not why it's over this large range. Another thing I'll mention is that if you heard Pablo Herrero's talks last week, you would have had a much more jumpy behavior in the Hall signal. Every time you get to 1 electron per Moiré, 2 per Moiré, 3 per Moiré, there would be discontinuities here where the system would polarize and form, in some cases, an insulating state. But in any case, here there's no, it wouldn't be fully visible in the Hall signal, but I can say there's no evidence of polarization. And again, that's not surprising here. This band is broader than the Coulomb energy, and so it's not too surprising that the Hall signal does something relatively simple. So, but we've learned something on this strong magnetoresistance is occurring near Van Hove singularities. So now it's time for me to show you the sample, and you can see that this is a somewhat more complex and rich sample than the ones that we started with. We've learned how to make it big enough that we can actually put 20 electrical leads on and thereby probe different parts of the sample. And we've built electronics that allow us to do all of this simultaneously. So we can measure longitudinal resistance on 8 pairs here, 8 more pairs there, so 16, and then also 9 Hall pairs, 25 of them. We can measure all of those simultaneously so that when we sweep the magnetic field and gate voltage just once, we can collect information about all these different parts of the sample. And that's really useful because it turns out the sample is not homogeneous. And this is common in twisted bilayer graphene. So what you can see is we can extract electrically information about the twist angle, and you see that the twist angle is not constant, but actually varies over the sample. So if we go through all but the very outer contact pairs, you can see that there's a variation of about 1/10 of a degree in twist angle. And if we look at the magnetoresistance is very different in the different, it appears in all these contact pairs, but it's different in the different pairs. And it seems that it's probably peaked around a particular angle. I'm just showing you on the sample that there's yet another surprise. One small region of the sample shows superconductivity, which had never been reported this far from the magic angle. So its superconductivity had been reported up to about 1.2 degrees in twisted bilayer graphene with boron nitride, but not at close to 1.4 degrees. So there are a lot of things that are strange here, and I'll have to say I have nothing to say at this point about the superconductivity, except that there are more mysteries lurking. But I can say something about the rest at long last. So so we had identified these crossings and tried to describe them phenomenologically, and then and we had been bringing these sorts of data to every theorist we could talk to, and they all said, "Wow, beautiful! I've never seen anything like this before." We also brought them to experimentalists, but I have no idea what's going on. And so my student, Joe Finney, who is quite resourceful, said, you know, while I'm puzzling over this, let me just, for play, let me calculate the Hofstadter model. So magnetic field threaded through a periodic potential where you have hopping in two perpendicular directions, and the magnetic field adds phases to these hoppings. And so this is something that's been calculated countless times, but just as a toy project, decided to do calculations on this and to see what would come out, and could he maybe tweak it and see some of these behaviors. So let me say what the behaviors are. I told you that there's this really ornate crossing that each of the split levels has a jump as it crosses the other. So let me just tell you a little bit about the Hofstadter. This is called the Hofstadter butterfly. This is energy on the vertical axis, and magnetic field on the vertical axis, energy on the horizontal axis, and actually, let me think. No, magnetic field is horizontal here. So you can see that energies start to split as you go out in magnetic field. In any case, this beautiful fractal structure isn't what we measure. We measure not in energy space, but in density. So I'll step you through how this works. But in any case, the Hamiltonian here is very simple. It's just hopping to nearest neighbors. And I'll skip ahead. Joe played with some of the simplest adjustments he could make to this. He could say, all right, the hopping in one direction is different strength from the hopping in the other direction. And he also said, let's add next nearest neighbor hopping, which effectively doubles the unit cell. And these were two of the first few tweaks he started putting in and calculating this. And here's what it produces. So I'm now showing things both in magnetic field and energy space, which is where here is the energy of the charge. I guess the charge neutrality point is at one end here. So this is an energy space and flux. And here Joe mapped this to density that we can tune with the gate electrode here from the charge neutrality point to full filling. And here's around half filling, and you see something's going on here. And remarkably, with these simple tweaks to the model, anisotropy and next nearest neighbor hopping, you get things that look a lot like what Joe is seeing in his experiments. You see these splittings of Landau levels as they go into a certain region around half filling. When the Landau levels cross, there's an ornate structure that actually, maybe I'll show you a zoom in, but that shows exactly the kind of behavior I described. And so this was sort of miraculous that it was, without any understanding of why we would get this model. And in fact, now is probably a good time to mention that this model is on a square lattice, but the actual sample should have six-fold symmetry. So it's not even the right, it's not just oversimplified, it's the wrong symmetry for it. So it was really remarkable that these all jumped out together, and there didn't need to be fine tuning. When we finally shared this further with the world by posting on arXiv, we got two good things that came out of it. One was Daniel Parker, who's a theorist at Harvard, pointed out that instead of next nearest neighbor hopping, we could simply say that there are two populations of fermions living on this lattice, and they have a different energy, different by some factor V. So that's a little bit simpler physical interpretation, and it gives the same behavior. And the other good thing I'll mention shortly. So in any case, we now refine the model. So we have anisotropy and two fermion species with an energetic splitting, and we get this nice match to the data without real fine tuning of the parameters. And I should mention that actually, if we look more carefully, it really seems that the splitting between the two species, it's a better description to say that it rises with magnetic fields, maybe like a Zeeman energy. So that maybe these are two spins, or maybe they're two orbital states. So here I'm just going back and forth between constant and Zeeman, and if you stare at it, you can see it actually, the Zeeman-like term gives a better description. But this was not very obvious. But if instead of going to a third of a flux quantum per Moiré cell, what if we could go to double that? Then the Zeeman splitting and the constant model look quite dramatically different. And so actually, in just a couple of days, Joe and one of my other students, Lindsay Rodenbach, are going to the National High Magnetic Field Lab in the US to open up this second part of the picture. In this case, to go to 30 Tesla, not 45, but they'll be able to answer that question. So I'm just going to skip over and let me do the, yes. There's another question. There's another question. Yes. So this is now on the honeycomb. So Nicholas, good and natural question. No, we have calculated on various other lattices, the hexagonal lattice and others, but it turns out that the honeycomb lattice is not the right model for this either. It turns out that the twisted bilayer cannot be represented in tight binding. There's what Senthil described as there's a topological aspect to the structure that says what you get out of the continuum model that McDonald and Bistritzer wrote down and described a decade ago is not actually describable in a tight binding model. So that was actually the start of why Joe used this simpler model. It was because it's actually quite challenging to do the continuum model, and in particular, as far as we know, it's particularly difficult to add the sort of adjustments that Joe added to the continuum model. So he decided to play with a model that he could actually, on his own laptop with a GPU, could do reasonably efficient calculations. So he was looking under the street lamp, doing the things that were easy. So why can we get something that's about right, even though we're not even on the right lattice? So first of all, the anisotropy that's introduced means that we're breaking rotational symmetry. So we only we don't have the original lattice's rotational symmetry anyway. And once you're breaking rotational symmetry down to C2, it doesn't really matter whether you're doing that starting with something with 6-fold symmetry or 4-fold. So that's lucky. And I think it's telling us that actually these behaviors are much more generic. It means that we shouldn't take very seriously the specific parameter values that we used, but anyway, those didn't need to be fine-tuned to produce these behaviors. You can fine-tune them, and actually we had a high school student working with us over the summer who really looked at what exact parameter values do you need to describe this, and I hope we'll have more to say about that in the near future, about how things vary as we go across the sample. But I think what this is telling you, that we use the wrong model and still get this behavior, it tells us it's rather generic. So I'm going to do the acknowledgements and then say a little bit about what we think might be happening and where to go from here. So as with the work before, my students Aaron Sharp and Eli Fox were quite involved, but this was led by Joe Finney. And this is the paper on archive that this is based on, that my talk is based on. So let me now just, right, I think I'm going to just stay here and make a couple of comments about what may be happening. If you remember, this sample was made by the tear and stack technique. And if you imagine taking a very thin membrane, say a plastic wrap, and tearing it, you might imagine that you would introduce strain. And so remember, there's what Joe needed to put into the model is anisotropy, different tunneling in one direction versus the other. We believe that that's coming from uniaxial strain. But we don't know that concretely, and so we want to study that more. Secondly, just as with the magnetic case, when we put this work out into the world, an experimentalist said, hey, I think that this looks familiar. And with the magnet, it was Andrea Young's group going back and studying a sample that had aligned boron nitride, but in this case, was Matt Yankowitz saying, from my postdoc in Columbia with Corey Dean and others, I think I've seen something with sort of this kind of magnetoresistance. And indeed, the number of, in that moment, the number of known samples in the world that had this property doubled. I'm pleased to say that just in the last week, in an attempt to reproduce this, finally, the third time, we've actually, instead of finding something new, we actually have been able to find another sample that has all of the hallmarks of this. So we're going to the National High Magnetic Field Lab with 2 rather than 1 sample. So just to summarize, we think that what's going on is uniaxial strain. That's not something that is generally controlled in stacking right now, but it's something that I hope we'll be able to get more control over. And it's just showing how many surprises may lurk, just next to what everyone's been focusing on. And so I consider this extremely hopeful, but it also means that there's an imperative to try to be able to make samples in a more controlled way. And there are many steps that people are taking along these lines. There's work at Brookhaven National Lab that was launched by Amir Yacobi that's aiming to replace students with robots. And that's, in this case, a good thing. In the end, students and other physicists will be studying the resulting stacks, but they're trying to systematize the making of each part of the stack, but they're still going to be exfoliating from bulk crystals, and we'll get randomness there. And so so I think that's going to be very impactful in the coming years. But my colleague Andy Mannix and I are going to try something that's a somewhat bolder jump that's based on his work as a postdoc with Ji-Woong Park at Chicago. And that's trying to do stacking based not on exfoliated flakes, but based on large area CVD grown flakes, like we're used to, what CVD grown films, like what we're used to doing in the semiconductor world, and doing stacking in an automated way in vacuum based on those. And our stacking system is in progress. It should be completed in the next month or so. And so I hope that next time I meet some of you, I'll be able to say, now we're able to make 100 basically identical samples, or 100 samples where all we changed was the twist angle, but we really carefully controlled the conditions for everything else. So that's what I think will be the, what I think and hope will be the path ahead. And I have no doubt that even if we stop having our fallible students doing the peeling, I am sure that we will continue to stumble on surprises in what we thought was a well-explored neighborhood. So thank you very much, and I'd be happy to take questions.
Thank you, David. Thank you very much for this talk. I see no questions here in the Q&A box. I see no questions in the Slack channel.
Yeah, I think that.
Yeah.
Yeah.
If there are no questions, maybe I have one. So it's a very general question. I don't know, do you have any insight, or you mentioned that you are also working on ways to have more control on the alignment between the layers. Do you have some idea of which techniques are available in order to determine the crystal orientation for nitride?
So Reyes was asking, I guess there are two questions implicit there. One is, how do you control the alignment very precisely? And the other might be, what targets would you be shooting for? Or can you specify which you most want to know?
No, the second, well, no, I think it was all the same question, because I think to determine the alignment, to some extent, you need to know the crystal orientation of your flakes.
Yes, so as long as you're trying to align on one material to the same material, the brilliance of what Pablo's group came up with, and separately Emmanuel Tutik's group came up with, this tear and stack technique, is that you don't need to know the crystal orientation of that layer. You just need to put together two parts of the same layer. And so as long as you're just working within one material, that's fine. But it's not okay when you're going from, you're trying to align graphene to boron nitride. There, I told you last time, there are lots of pitfalls, because you have to go by facets, and those facets you can't tell to better than a degree or so. And you could be off by 30 degrees because it could be the wrong facet. So you're right that there are ways to ascertain this. So first of all, you could try to do crystallography. You could do diffraction and determine the orientation of each of the crystals independently. And we do plan to do that in our next generation UHV system. We plan to have those sorts of tools. But you can also use more some commonly available tools. So probably many people in this room are familiar with Raman spectroscopy, which tells you about the vibrations of a crystal that light can couple to inelastically. And it turns out that Raman is sensitive to twist angle between two layers. And so you can learn something about that, although it gets awfully complicated if you have boron nitride, graphene, and graphene. But if you have just two of them, there's a literature on what you should see in Raman, and it's somewhat informative. You can use second harmonic generation. That gives you some information, especially in things like boron nitride or transition metal dichalcogenides. So there are some tools that you can use, and that can save you from having to, cool down many samples to find what you're looking for. Instead, you can check, do you have the structural motifs that you're looking for? But it's really tricky because in the fabrication process, you can get twist changes. The system really, really wants to be aligned. It doesn't want to be at a small twist. And locally, it will realign. If you have a twist angle that is a degree or so or smaller, so right at the magic angle or smaller, you get substantial local relaxation, realignment of the lattices so that they're locally aligned, but they're still stuck globally. But a significant fraction of the time, you'll actually see a global realignment, that the one flake will macroscopically rotate to lock in with the other. And so you really need to do your characterization as much as possible on the actual sample you're working with, and even in the device structure, and that gets challenging. So I think that there are no magic bullets, but I do think that there are some tools that you can use to give yourself a better chance and to know whether you've succeeded. So that's, yeah. I just want to say one more thing. I know it's the end of this, but remember this first thing that jumped out for us, the magnetoresistance. I showed you that there was something that seemed to correlate to that in the inverse density of states that I was plotting for the Hofstadter structure with these extra terms. But I have to say, the Hofstadter structure is just a spectrum. It's not a calculation of conductance or scattering. And we still don't fully understand. We've been planning to do a Kubo formula calculation to try to see, can we get this strong magnetoresistance from that model? But I would say that's at the moment open and out there. And so if there's anyone who's excited for a small toy calculation that might reveal something, I think it would be really interesting to understand why we actually see this strong magnetoresistance over a large range of density.
Okay, thank you. There is actually a question now in the Q&A box.
Okay, great. Yep, So the Hofstadter model you used, this is from Mikhail Garcia. Thank you, Mikhail. Welcome back. Mikhail asked a couple of good questions last time. The Hofstadter model you used is just a single square or triangular lattice. That's right, that's what it starts with, but then we add anisotropy. So on the square lattice, that's easy to think about. Its hopping is different in one direction from the other. So I'll just go back to, so we add anisotropy, hopping different in one direction than the other. On a triangular lattice, you can do this by making one of the three directions different from the others. And then we also add a splitting in energy between two species of electrons, which right now we don't know. It could be two spins, it could be two orbital states. And so maybe just as a, so yes, Mikhail, this model started life as just a simple square or triangular lattice, but we added on, Joe added on a couple of small components to that. And maybe this is a nice way to complete the circle. There was a question earlier about whether, that was from Danielle, about was our magnetic field perpendicular or in the plane? And so all of these things are changing the hopping, the phases of the hopping, so it needs a perpendicular field. But now that we see this splitting between two species, you can ask, is that spins? So Nicholas asked, this is now in the honeycomb. Oh, sorry, that was old. I apologize. We have this splitting between two spins or two orbital states, we don't know. And so to look at that, we might want to see what is the effect of an in-plane field. And we did just a very quick measurement before going to the magnet lab, putting the biggest in-plane field we were able to in that cryostat, which was 4 Tesla, and the effect of the in-plane field, a perfectly in-plane field, was nothing. So we do want to combine those and ask what happens if you have an out-of-plane field, but you also add a big in-plane field. So if what you're splitting is spins, they should be split more. That's something that we hope to do in future, but the jury is out about whether the objects that we're splitting are orbit spins or something else.
Thank you, David. I actually have one question.
Great.
Related with the beginning of your talk. You showed a plot, the magnetoresistance versus the film, and close to the charge neutrality point, there were some wiggles, and they look symmetric. That one, yeah, does exactly. Those wiggles are merely noise, or do they have any meaning?
Oh, no. So excellent question, Santiago. So those are actually Shubnikov-de Haas oscillations, which we're seeing here. So these are the successive filling and emptying of Landau levels, and we're seeing it here as a function of carrier density.
Okay.
You can see that they shift a little bit with magnetic field, and if we look at this plot, you can see they're just cuts through these Landau levels,
okay.
but we're doing a cut in this direction.
Okay. So, yeah, perfect. Thank you. Thank you, David. I see no more questions in the Q&A box. And yeah, so on behalf of everyone, I thank you again, David, for these talks, for being with us in this topological summer school. And of course, you are kindly invited to come here in person next year.
Yes, I wish that this had been in person rather than virtual, and may we soon be in a situation where that's safe and we can rejoice in talking together over beer.
Yeah, for sure. Thank you again, and we see you soon. So we close the session, and we expect to see you again, guys, tomorrow at the same time. Thank you. Ciao.